help me welcome Oscar, who is going to be talking to us about AI and TinyML. So let's give him a nice warm welcome.
Jesus. Alrighty, thanks very much. I'll wait for maybe one or two people just to sit down here and then crack on. Alrighty, so give it a second here. Thanks very much, everybody, for coming and taking the time to listen. There's a couple of other interesting talks on, so I appreciate you just coming to sit to this one. Context of this talk is that it was built for a university module where I was using AI with an Arduino TinyML kit to build something that would help progress the UN's SDGs. So I was limited by various constraints of the module, like having to use certain hardware, which we'll kind of touch more on later. But the hope from this talk isn't that you'll go away and build this solution. It's more that, you'll go away and kind of, it'll give you a bit more thought about how easy it can be with AI to build a positive solution that could progress, say, the UN's SDGs. So, speaking of which, with it being a final year of uni, this talk has been pretty thrown together in the last week. So you've sat down now. There's no getting up without hurting my feelings. And you're on this roller coaster, so just ride it out for the next half an hour. So, first thing, again, context-wise, and a disclaimer, if I had solved food insecurity, that would be me at the Nobel Peace Prize. That's not me. I'm at NIDC. Thank you so much for having me again. But yeah, this talk's kind of more about realizing how AI can have massive benefits in, positive work in an easy way. If we can look for the applications, it's not me solving food insecurity in half an hour. So, the problem that I was addressing is the effect of poor soil quality on crop yield. Again, the first 10 minutes of this are going to be very soil heavy, so try and keep it, try not to fall asleep. It gets interesting in 10 minutes. So it's specifically in relation to the disparity between farmers who are farming in more developed countries and LEDCs. So generally LEDCs have slightly worse infrastructure, less capital to invest in specialist equipment. So there's various issues where there can be, you see a farm in the Netherlands and you see a farm in an LEDC and it's not going to look the same. So reducing the quality of soil or nutrient loss can cause crop failure, malnutrition, which is detrimental to farmers and LEDCs who depend on a consistent yield to provide for their families. Providing these farmers an affordable and easy way to measure the quality of soil so that they can tell the soil, if it'll cause their crops to fail or if they'll have a better chance of a consistent and a full crop yield. So we're working towards kind of SDG 10 and 8. So that's reduced inequalities and decent work and economic growth. So, solution. Climate change is increasing the number of droughts and floods. So this will impact soil moisture and therefore crop growth. So continuous monitoring of the temperature, humidity, soil moisture content using the built-in sensors in the Arduino and using the camera module will allow farmers to sample their soil in different locations around the farm and then scan these samples to estimate the soil moisture content. So they should be able to proactively improve irrigation, change watering schedules, and it'll be especially impactful in regions where water resources are limited, right? So the changes will have a great impact on soil health, which will directly increase crop yield and prevent soil degradation and nutrient leaching. Went for this approach because I wanted the solution to be low cost, easy to use, as research shows that the advances in technology are not always viable for small to medium-sized farms due to lack of capital or education. So additionally, this solution will be low energy, which is good for farmers who don't have reliable infrastructure in place. So it shouldn't change any of their, historic farming practices, which is good for culture and things. So we could set this up and kind of have, loads of these Arduinos around if it's a large farm, or if it's a small farm, we could have a couple in each corner, and they can then be alerted if, say, at the bottom of the farm, it's an absolute, mud everywhere, water throughout the farm, and the top of the farm, if it's really dry, if it's, say, a farm on a slope. So they can then be alerted about that and use that to change irrigation schedules, etc. So I did a dry run of this talk to a friend. His question at the end was, I've got a better solution. Get the farmers to lift some soil with their hand and feel if it's damp or dry. And they can use their Arduino for some nice Christmas tree lights. So as I'd said, this is one solution. It's definitely not the best solution, but it is a solution, and a bit more the talk will be a bit more about how I built this rather than what I've built, because it's questionable about whether you would use it, but we'll get on to that in a second. So the collection of data is really important for an AI model. Generally, the rule is if you're getting a poor response from an AI model, you either need to fix the data it's trained on, or you need to fix the prompt that you've used. So bad data equals bad results. I needed to make sure that the data I used to train the model was both accurate and varied. So whether you're using AWS SageMaker, Vertex AI and GCP, or like me, I was using Edge Impulse. If you're training a model, the data needs to be accurate, varied, and free of bias, ideally. So here's a fun little video on my data collection, which again, this is a university project, bear in mind, and I'm actually going to turn down the volume a tiny bit if I can. There we go. And I'm going to pause it at certain points as well. This is me in the back garden. So to collect the images of the soil, I use the following steps, which you saw at the start. Clean the trial, clean the plant pots, avoid contamination. Again, there's a lot of little pernickety steps about this, which is always to try and keep the data as clean as possible. So taking 3 samples, measuring them out, 100 grams of soil each from the back garden, and the soil used specifically here because research shows that the physical properties of soil when it's fresh, as opposed to being planted long-term, are actually very different. So, oh no, go back. We don't get to the fun stuff yet. We're still in the bad stuff. Yeah, so, yeah, very different comparison. So, oh, I'm gonna turn that again. There you go. So, then I used a hairdryer to dry it out completely, as ideally it should have taken 20 days of room temperature to get the soil dried out so that I could have a consistent measure, and I wasn't up for waiting 20 days for uni coursework. So they all needed to be 0% moisture, ideally, and then I got about, say, 60 milliliters of water per 100 gram to one pot to simulate a good level of soil moisture. Then I had about 80 milliliters of water per 100 grams for overwatered soil, and then was taking photos of those up close from different angles, varying light levels, to make sure the data set is accurate and varied. Oh no, can I stop it there quickly? Yeah, no. That's just bad luck on a live thing. Right, let's see which bit of this is best. So about here, you can kind of see where I'm collecting the data set. So you can see, I'm going to show a better photo of it, don't worry. But you can see I've got the Arduino in my hand, I've got the plant pot below me, and I'm taking a photo of, and it looks like an excellent photo at the minute, of the soil in the plant pot. This is me adding the test data, so I'll label each piece of test data and add it to that data set on Edge Impulse. Okay, so enough talking about soil, on to the interesting AI bits. So I used something called Edge Impulse. So it basically is like an online, it's a website you can go on to connect up your IoT devices, and I was able to train a model on that for my Arduino and then actually deploy it locally on that Arduino. So you can see some of the interesting things you can do on the side I've kind of highlighted. You can create an impulse, which would be your model. You can then add each image individually. You can use transfer learning. You can add more images and then retrain the model. You can do live classification. So I've trained my model and then I want to test it. So I can get another plant pot, put a load of dry soil in it and say, what does this look like? And test the model and see what it comes out with. And then we can do some extra model testing and then deploying it locally on an Arduino. So we can, have that on the Arduino, give it to the farmer and say, you don't need to have it plugged into the computer or the Wi-Fi or Edge Impulse. It's a proper IoT device and the model is working on it. Bear in mind though that a lot of these Arduinos have I think it was maybe like megabytes of RAM. It's tiny, tiny, tiny. So the model that we're using has to be very small. So showing you the test data a little bit closer. We added each of these images and then we would label each of the images so that then the model can use that for test data. So that's kind of the screen that we were using for that. And in terms of implementation, we had 4 steps. So that was pre-processing, feature extraction, modeling approaches, and validation methodology. So for the pre-processing, you can kind of see the block here. I'll show you at the end what the proper website looks like, but you can see the block here and I've just screenshotted each different step of it in the create impulse step. So we use the image option to pre-process and normalize the image data. So all the images are resized to a consistent size, and I've chosen to squash the images instead of crop them because you want to keep as much of, ideally, the data in the image as possible. The color depth, I also selected for RGB instead of grayscale. The reason for this you'll kind of see in a second. You can use grayscale and turn all the images, obviously grayscale, but the problem with that being my solution was based on the color of the soil, basically, its physical properties. So using grayscale might have affected the accuracy of the model, and change the color so the water saturation would look even more subtle in grayscale. Next part of it was the transfer learning. So the definition I got from Gemini, which has said transfer learning is a machine learning technique that uses a model that's already been trained on one task to improve its performance on a related task. So it's basically what I did. You can see there, I've got output features, and this, literally, it's a no-code solution. I've just gone on and just created a little block, told it to do it for an image, and it's going to do transfer learning for us. And the feature I decided to focus on was obviously the shade of the soil. So that was to determine the soil moisture, as this is the most prominent physical feature I could measure. So the features I used, as you can kind of see on there, are damp, dry, waterlogged. So dry for underwatered soil, damp for soil that was an ideal soil moisture, waterlogged for soil that needed irrigation, and then an extra feature called unknown. So this unknown feature was to prevent the model from wrongly attempting to classify images that were taken poorly or images that were taken by accident into one of the other classifications. So I also attempted to prevent leakage by taking images close up so the model didn't have access to any information that it shouldn't use to classify the images. So that would be, for example, if whenever I was taking the photos of, say, the plant pots, I had one plant pot which was dry, damp, waterlogged. If the plant pot for dry had a little mark on the inside of it, and I trained 100 images on this plant pot with dry that were all labeled as dry, and then say the waterlogged one had a different kind of mark and the damp one just looked fine, what it would do is then it would be leakage. So it means that our model would actually not be looking for the physical properties of the soil. It would be looking really for that mark. So it would see that mark and it would automatically say, okay, that's the dry soil, because that's on all the images I've been trained by. That's one of the important, pieces of information that I've seen. So to kind of stop that happening, we made sure to take the photos close enough in that really it was just soil in the photo instead of, getting anything else. So then we had the modeling approaches. So for my model, I fine-tuned a pre-trained image classification model and then used my data instead of creating my own model. This would have made it a lot faster and performance much better because I was using a small data set. So it's important when deploying on the Arduino because I need to make sure that the model was not too big. And I leveraged transfer learning to train a neural network to improve performance of the model significantly. So you can see at the bottom, you've got the model. There were much better models on Edge Impulse, but the problem being, I think it was something like 8 megabytes or something stupid, like 32 megabytes of RAM is all that you got in the Arduino. So if we're already using a machine learning model and then we are fine tuning it, which basically just means taking that model, using our really only 100 pieces of data, which is like 100 photos of different soil samples, and using that to fine tune that model to our exact context. And you can see at the top, you've got number of training cycles. So that's to do with how many times you iterate over that data and train the model with that data. So you could have done it 200, you could have done it 50. 100 was where I found the best match. You know, with different models, it could be different. With different data, it could be different. You ideally don't want to overfit the data. So you don't want to have so much data or run so many training cycles that actually, as I'd said a second ago, it's no longer looking for physical properties of the soil. It's looking for, you know, there's a little leaf in that soil sample. And now that you've taken 200, 300, 400 photos of that one sample, it's really only looking for the leaf. It's not looking at the physical properties. So you don't want to overfit your model to a specific data set, because then it'll just be looking for specific little bits of that data, and it won't be varied enough that if I bring it, you know, a different soil sample from somewhere else that is dry, it won't pick up on that. So that's the training cycles, learning rate, training process, or yeah. Okay, so that's that done. So for the validation methodology, I decided to use generally recommended test train split of 80-20 to validate that the training has been successful and allow us to evaluate it. So I'll talk through the, oh, that's terrible. It's just green, isn't it? There's about 4 different shades of green there, but we'll not worry about that. Yeah, I'll talk through the metrics and things on that in a second. But the first time I tested this, I found, for example, that the dry feature had 0% accuracy. So you can see there, at the minute, the dry feature looks great, 100% accuracy. First time I did it, it was terrible. So what the problem was then, you can go back and you can just look through, you can see, right, some of my images were inconsistent, some of them were maybe a bit blurry. So I was able to go through, clean the data set, delete the blurry images, add more images to the data set to try and train it a bit better on what a dry image looks like. And then increase the accuracy to ideally about 80% or above. I think if you're getting too close, like if you're getting 100%, your model is possibly overfitted. But you want to try and stay as accurate as possible. So talking through this data, which you can see whether it's probably red or green. There's 4 different shades of green, but that's not important anyway. We'll not worry about that. Basically, you can see that there's little clusters in different places. There's a cluster, say, there, and there's a cluster there. There's a bit of a cluster there and a cluster there. And that's important because it's picking up on certain features. So it's picking up that, you know, all of these in this cluster have very similar properties or features that we're able to recognize and cluster them together. And the same with that one. So whether it's damp, say, is over there and dry is over there. And then the unknown ones are just kind of spread all over the place because they can't categorize what feature is what. So that's the data explorer, which you'll get whenever you train the model, which is really useful. And then you've got a confusion matrix on the bottom, which is used for basically looking at the accuracies of the test train data. So I've trained it and then it goes through and it says, oh, well, actually, you know, we looked at the damp ones and 100% of them we guessed were damp for the training data. And then we guessed the dry ones and 100% of them we thought were dry. But then we looked at the unknown ones and actually we guessed those wrong. We thought half of them were dry and we got half of them right as unknown. So it gives you a better idea of how accurate and where the classification problems are happening, because you can see there the damp data and the dry data is fine and the waterlogged is fine, but it's unknown that it's getting a little bit annoyed about. So I can go back and actually look at that classification and see what I can do to improve that. Yeah, that's all that done. Alrighty, so this is the demo, which I think should be fine, but I'm gonna hit pause on it at a couple of stages. So I've set the confidence thresholds to 70%, which basically means that whenever we scan a plant pot, you can go through. There's no way half of you can see that, but I'll read it out for you. So this is that live classification that I was talking about. So I've got the plant pot, I've got the Arduino, I'm taking a photo inside the plant pot of the soil, and that's the image it's showing. If you're looking image quality, don't buy an Arduino. They're awful. Or buy a better camera. You can see that I've got my 4 different categories. We've got damp, dry, unknown, and waterlogged. And it really doesn't think it's any of the other ones. It thinks it's damp. It's about 89% sure. With the other ones, you can see it's got about 2% similarities with dry, about 3% with unknown, and about 6% with waterlogged, which makes sense because waterlogged and damp will have some similarities. So you've got the features there, and you can see that whenever we've tested that, we can actually add it. If it's over 70% confident, which it is, it's 89% confident, we can add that to our test train data set after the live classification. So solution I've implemented works well. However, you'd need a good torch because whenever you're looking in a plant pot, there's barely any light in it. So you can see me holding my phone's torch above it. But that's generally how it works. And you can see kind of at the end there, we had a bit of a difficult one where that's the image of the soil and it can't decide whether it's damp or waterlogged. So it's not giving me a response because the confidence thresholds are set to 70%, which generally is about a good number. But it's 50% sure it's damp and about 45% sure it's waterlogged, which again, as we said, makes sense because they'll have similarities in their features, but more training needed to make sure that it can very accurately determine individually between them. What's next? Evaluation of solution. Alrighty, so future improvements. I'm sure you're all thinking of several future improvements, but the ones that I'd identified, sensor fusion. So ideally, it'd be nice to have this model use humidity or a couple of other, metrics, say humidity and temperature data, as well as the visual data. So to improve the accuracy of the model, the problem is whenever I tested it with temperature and image data, it has the opposite effect. So you have to be really adding extra sensors is brilliant and in theory should increase the accuracy, but realistically, if you're not spending a long period of time on it, you have to get it right. It's really difficult to train a model on sensor fusion because you're bringing in one data set and telling it this is good, this is bad, so that makes sense, but then bringing in another data set to try and relate those to each other. So saying, what's the relation between humidity, temperature, and this visual data? And at what stage is that a positive? Whenever we have high humidity and low temperature, is that a positive result? Or is it whenever we have low humidity and high temperature? Trying to get it to where it knows what's good and bad at each of those different kind of mixings of them is really difficult whenever you're training the model. So it just takes more time. And again, as I said, university coursework, I don't have 2 years to spend training a model. I had probably 6 weeks or something. So that was what I decided not to do sensor fusion, but it would give us much better accuracy if we did take the time to train it. What else? Create a data set which uses more soil types and soil from actual areas around the world. That soil was my back garden. If I went to Africa, Asia, there's 7 different types of soil. It's probably not going to work. It might have a good go at it, but who knows what it would do. pH sensor, again, for kind of more sensor fusion, using a pH sensor or a soil moisture sensor would have just gotten rid of the whole AI problem in the first place. Soil moisture temperature or soil moisture sensor would have just told us the soil moisture senses, or the information from the start. So, really it wasn't about getting a good solution. It was about how do we use AI to build something that could be useful for the farmers. What else is there? Yeah, I did consider using soil moisture sensor, but also they're specialized sensors. They can be very expensive. And the point of this is for it to be cheap and easy to use for farmers worldwide. Is there anything else? Yeah, the pH sensor would have been useful because we would have been able to recommend adding lime if you're if the pH was off and you needed it more acidic or needed more acid, you could add certain things just to very easily change that, which again would have a big impact on your crop yield. But again, low cost. So, does anyone have any questions at this stage? I can run through it one more time now that we've got through everything, so that you have a better idea of kind of how it's actually all come together. But does anyone have any questions?
Hello. With your unknown categories, is there a way to tell the model this is the category that you put things in when you don't know, or is it fitting to that in the same way that it's fitting to your real categories?
I have a feeling for the unknown category. I just took photos of the wall and like random things. So using Edge Impulse, I don't know that there's a way. I had to create that category myself, create that output feature myself. So it hopefully should have worked quite well. The reason being because it should look at those other 3 categories, which have really stringent features. And it should say, okay, it's not any of those features. It's not any of those features. This category doesn't really have any stringent features or any classification that I can see. So I'll just put it in that. But yeah, I see what you mean. Not 100% sure if Edge Impulse provides that. Wasn't something I saw, unfortunately. So no worries. Any other questions?
I'm just wondering, would you be able to stick a solar panel on it? Do they do like tiny ones, or is the Arduino a bit too powerful to be powered by that sort of thing?
How, as in stick the Arduino into the solar panel?
Or, power it with solar power.
You probably could.
Kind of low energy.
No idea, but you probably could. We had just little, those thick batteries. We had just fired those onto it. That you could so you could probably just fire on any connection you want. We usually just had it plugged into the Mac and just, powered it via that.
Yeah, fair enough.
But I don't know of any constraints.
Yeah, no, firstly, very interesting talk, thank you. So you sort of mentioned in your talk there about deploying AI and Arduino probably isn't the best choice because you can have overutilization of resources. One thing I want to check, did you do any sort of like optimizations to your model so it could deploy in the Arduino, like quantization or anything like that?
We didn't. So the only thing really to keep the model smaller was that fine tuning of a pre-trained model. So that was just like the only thing to try and keep it as small as possible. We didn't train our own model. We just fine tuned an image classification model already and used a small one so that it fit on the Arduino. And that did work quite well. We couldn't use one of the bigger, more accurate models, but as AI progresses, the models become smaller and more accurate. And that was probably 6 months ago. It was August time. So yeah, it was probably 3 or 4 or 5 months ago, maybe whenever I was building it. So I would say it worked well enough, judging by the accuracy things of it, but I didn't use anything else other than use a small model and use a pre-trained classification model. So we could just use the 100 data points on it to retrain it or fine tune it. So does that vaguely answer the question?
Oh, yeah.
Sweet.
Thank you.
No worries. Anyone else?
On Impulse, what level of customization did you have in your classifications? What I'm thinking of in my use of ML, you're using the confidence threshold. If I was say I had 2 that were summing to be above the confidence threshold, I would classify them myself as having 2 predominant groups. So I could say, well, it shares the characteristics of both damp and waterlog. Is that something you could do with that with more time, or is it sort of strict in how you use it?
So really what you're saying is if the confidence threshold was 70% and we got damp and waterlogged both back as 75, you would then have said that it shared those features?
I mean more so, say you had 50 and 20.
Okay.
So, it's not over your confidence threshold for one group, but it sums to be, between 2 groups, it sums to be, so it seems to share the characteristics of both. Is that something you can do in that setting using that bit of software?
Not sure. It's quite good, and like everything I've just shown there was free, other than the Arduino, obviously the hardware. So everything I did on that was, free to use on Edge Impulse. So in the pro features maybe, but from what I saw, not currently. Although it is, it's a no code solution, so there's not a huge amount of customization, but there is a little bit, and you can play around with it a bit, and it's a nice, easy to use. But I didn't see anything like that, no.
Brilliant, thank you.
Sound. Class. Well, if I go through very quickly. There's the thank you slide. So, wasn't that exciting? Thanks very much for listening. Taking the time to come here instead of the Furby talk, because it was probably more interesting. So. And if anybody wants to do more information about this or doesn't believe half the stuff I was saying, there's a lovely list of references for further reading.